Hello, everyone. Can you hear me?
Yes, we can.
Okay, so let's start. Today we will study about one methods that can help us to work with generation. Okay? It is VAE. So up to now, you may experiencing about with many systems or many apps that can help you to generate some image or videos with a very high quality, right? For example, for image, there's many systems. Some years ago, we have Midjourney for imaging, or now many systems like ChatGPT or some other system can help to uh, to to draw some picture or image very easy, right? Or even in the case you want to generate video, they can help you to generate one with a high quality, very easy, right? Just by describing some words about the content of the picture or video, right? Okay, so what is inside those systems? How can we generate those things? Okay, so in this lecture, we will study about some idea how we can use some models that can help us to generate something, right? And those systems can be considered to be generated more. But what are they? We can consider them to be some model of the data. And if we use a probabilistic notation, we are using some probabilistic model, right? Uh, and those models can help us to generate or sample some new example, right? Sometimes they can help us to evaluate the likelihood of a given example. Or sometimes we need to work with training, or sometimes we can use them to learn a new representation for the data. Those are some tasks that we may work with when we use a generative model. And of course, this task has been studied a long time ago, at least in statistic probability, for example, and recently in AI. And in AI, especially in machine learning, one very interesting task is we focus on sampling. That is, how to train a model so that we can use that model to generate new sample with a high quality. That is sampling. And in the last 10 years, 15 years, for example, many breakthroughs come from these problems. And up to now, we have many systems that can help us to do very good things, right? Okay, so before studying about some specific models, we first remind some concept in probabilistic model. Okay, so what's that? Essentially, one model can represent our assumption about how the data were generated. Why we can consider something like this? To see this, let's take one example. Every day you may say something, right, in a meaningful way, and each time if you want to say something, you need to speak one sentence, for example, right? So let's think how your brain can use a sentence in order to help you to speak, for example. It is something like this. For example, how about you? If you want to say a meaningful sentence, how can you do? How did you do? How often you do? Okay, so just say one meaningful sentence. So what is the sentence? Just say one. Random sentence. Okay. Is it, um, how about the girl? Can you say yeah? Can you say one sentence? Hmm. Today I attend this class. Okay. How about your brain? How can it produce a sentence like this? Mm-hmm. Okay. So to say that sentence, did you do something like this? First, you choose a topic you want to say, right? Or the message you want to say. And then you can generate some words that describe the topic. Okay. So this is just one example. And every day we can often generate many sentences and you will speak with many other people, right? And it means that your brain produce many different sentences in this way. So you can imagine that your brain, it is in fact a generating a system that can produce some sentence, right? Produce data. And at least it do these two main steps in order to have it to speak one sentence, right? Okay, let's take another example. You want to draw a team like this. How can you draw? Can you take the drop and draw in on drop? Can you draw? No?
Sorry,
Can you
can you
take
expand on the
the exercise? Please draw a team. Okay, so I hope you have your results. Như Thái, do you have? Can you share your drawing?
Could you wait a second? Give me a minute.
Can you share your results for the exercise?
In the chat group, right?
Yes.
Give me a second. That very simple draw.
Is that team?
Yeah. That is a team in my imagine.
Okay. How about Đinh Hương? Can you share your results? Đinh Hương, are you here?
Sorry, can you hear me?
Yes.
Can you explain for me what is team mean? I don't know what it exactly is.
You're asking about the exercise?
Yes. I don't know what is TIM is. I don't know
Okay, so,
the definition of it.
the
So can you
exercise,
explain for me?
the exercise is a draw team. Here is team, right?
Oh, just minion.
Okay, so the exercise is draw team.
Oh, just the character in the movies or the cartoon, right?
Yeah.
Okay.
Okay, Hướng, can you explain how to draw a team? How did you draw?
Oh, just so can I speak Vietnamese?
Try English, please.
Just the first I draw his eyes. Uh, After that I draw a circle under one circle and two hand and two leg.
Hmm? Oh, so in the past, did you study how to draw?
For sure, no.
Okay, so that's why. How, Tuấn Anh, how do you draw?
Just simply, I draw about his how to say his leg, his hands, his eyes, his hair, his mouth, and anything that I can see, and I can draw like that.
Oh.
It's not follow any these rule or any structure. It's just my freestyle.
Okay. So it seems both students haven't studied how to draw before, right? Okay. If you study before, you may have some way to draw a team like this, for example. You can do many steps. For example, in the first step, you draw the shape, and then in the next step, you sequentially fill some details about team, for example, until you have the complete picture, right? Okay, so in this example, this is another example to show that in practice, each picture or each data sample can be generated by some process, right? For example, for this picture, it can be considered to be one data instance or example, right? And in order to have this example, you need to do many steps like this in order, and then you can get one picture, one data sample, right? So in this example, you can see that each data sample can be generated by some process, right? And machine learning are trying to recover or approximate those processes. If we use some language from probability, for example, we will work with this kind of model. Okay. Okay. So when we use some notation and concept from probabilities and statistics, sometimes we will work with variables, right? And one variable can help us to represent something, right? If that variables can be observed in practice, sometimes we call that observed variables. But sometimes we're going to work with something that is hidden. For example, in the case, if we try to represent the words in a sentence, you can see that the words we can observe, right? We can collect each word in a sentence or in a document, for example. So you can use one variable to represent one word. So in that case, that variable should be observed, right? To be observable. But another thing, it exists in a sentence, but we cannot easily observe. For example, the topic, the themes, or the message, right? But it's hidden inside one sentence. If you have some knowledge, you can understand the themes or the topic of sentence, the meaning, for example. But in a case, if you do not have a good knowledge, then sometimes the sentence it is very hard to understand, right? So that's why if we want to represent something hidden in a data set, in a sentence, you can use one variables. And in that case, we can call that a hidden variable, or sometimes latent variables. Okay? Sometimes they can be very useful. And of course, in the models, it can contain many different variables, right? For example, we can use X to represent the words, Z to represent the topic or the meaning, for example, right? And then X and Z should have some relation. In order to generate a sentence, we first decide the meaning or the themes or the topic you want to say, right? And then you can generate many different ways to describe your message, for example, right? So essentially, in one model, we should have some variable, right? And there's some relation between those variables. For example, in order to generate one word, we need to know what is the message we want to say, right? That is, we need to condition on the theme or the message. So in this kind of models, each variables, it is a random variable, right? Or in other words, it should follow some probability distribution, right? Okay. So by those notation, we can build many different kind of models in practice, right? For example, we can build a model to represent how we can generate a sentence or a document, or how we can generate one picture, for example, right? It depends on your choice, your assumption. And of course, when we sometimes we can use some notation from graph theories to represent one model. For example, for one variable, we can use one node to represent one variables like this, and we can use connection, the edge that connects from one node to another node to represent the conditional information. For example, this variable is conditioned on Z, for example. And this relation should reflect some real interaction or connection between those two variables, right? Sometimes we use gray circles to represent something observable in practice. But in the case, if the variable is lit, we can use blank node like this to represent. Okay. Okay. When we use those notation for probabilistic models, sometimes we call probabilistic graphical model. Okay. Because here we use notation and concept from both theory, both areas, right? And of course, generative models, it is a group, it is a subset of PGM. We just focus on some models that can generate new sample in the future, right? After training. So in those cases, we call that generative model. Okay, so let's take one example. Assume that you want to model, or we want to know the average height of a person. The average height, right? So in order to know that in the world, for example, in practice, you can collect some people from different areas. For example, we collect 10 people from Hanoi, and then we can obtain a data set like this, right? And want to estimate the average height of a person. Okay. Let's take very simple model like this. We assume that we denote X to represent the height of a person, right? And now we assume that the height should follow a Gaussian distribution or a normal distribution. Okay, that is just our assumption. Sometimes the assumption may be good, but sometimes can be wrong, right? And when we have this assumption, it means that we already have one model, right? That is Gaussian model, right? And for this model, for this distribution, we can write density of the distribution to be like this, right? Here, mu represents the mean and sigma square to represent the variance of the distribution. And as you can remember, when we draw the density, the graph should be like this, right? And of course, we can represent this model to be by a graphical like this. X represents the height. It is observable, right? We can collect in practice. And X depends on two other variables, that is mu and sigma square, for example. This is very simple. Okay, so today is just one example about a probabilistic model, right? It is very simple. And in this model, it represents a class of normal distribution parameterized by two parameters, mu and sigma, right? And in practice, if we want to estimate the average height, it means that you are working with the learning problem. Or in other words, we need to estimate the specific value for mu and sigma, right? This is just one example for a simple model. And of course, up to now, there are many classes of probabilistic models. For example, in the past, we have very well-known models. For example, Gaussian mixture model, and recently, Latin-Dirichlet allocation, or hidden Markov models, and recently, deep generative model. Those are very well-known models, and sometimes they are very helpful. Okay, do you have any question?
No.
And when we work with this kind of models, we can work with some tasks. For example, sometimes you want to use those models to do inference, right? For example, you want to use those models to make some prediction. It is in fact inference. Okay, so what's that? Sometimes we have one instance xn, and then your task is to do some inference for some other variable. For example, for these models, you want to estimate or to make some inference about z. For example, xn here can be a collection of words that describe one sentence, right? And z here represent the topic or the meaning. Okay, so the inference task here is, given a sentence, please provide the meaning, for example, right? Okay, so in order to work with that problems, for this kind of models, you can formulate that inference problem to be to estimate the distribution of some local variable. For example, you need to estimate the probability of Zn given Xn and the model. Okay. For example, you need to estimate this quantity. This is the inference problems. Another problem when we work with this kind of model is training, right? Or sometimes we call estimation. And then the main task is to train the model based on a given training set, right? Okay, so those two tasks is very common for any other models. But here, we need to use some notation from probability and statistic to do inference or to do estimation, right? For example, the training phase can be expressed as a estimation of the density distribution, density function. For example, in order to estimate the density function of these variables, even though that you already know the whole distribution, right? Or sometimes you can estimate the probability that you can observe some data instant from x1 to xn, for example, right? Based on this quantity. And in fact, each models can be represented by some parameters, and the training phase is to find those parameters that represent the model, right? Essentially like this. And of course, when we do the training, inference for local variables sometimes should be done. Those two problems are very classical, and in statistics, they have been studied extensively. But recently, another problem that is very interesting, it is sampling. It comes from the needs in AI, in machine learning. What's that? We want to produce novel data sample based on a given train model, based on a trained model, right? That is, we need to use one trained model to generate new novel data sample. Okay, so that is a sampling problem. And of course, in practice, this problem has many applications, as you know up to now, right? It can help us to generate video, image, music, and many other things, right? But of course, it should have a lot of application in practice. Okay, so those are some ideas about probabilistic model. Do you have any question?
No.
Okay, that's good. So let's move to a specific type of those model we call generative model. Okay. So let's discuss more about how to train a generative model. In practice, we can collect a set of example, right? And we call that the training set. For example, we can collect some image about dogs like this, right? And then we want to learn a distribution from this training set. Or in other words, we want to train a probabilistic models from this data set, right? So that after training, you can use that model to make generation, to do generation. That is, we can take some new sample from the trained model, right? And the new samples should look like a dog. So in this phase, sometimes we call that sampling or generation, right? But sometimes these training problems can be considered to be a density estimation problem. And of course, this problem is very classical in probability theory and statistic. Okay, for example, in practice, we can collect some example like this, and the true density of the function of the distribution can be complex like this, right? And we need to find that based on a training set. And sometimes in practice, we can use those models to produce new representation for the data in a useful way, right? Okay, so essentially, we need to find one one distribution based on a data set, right? And in this data set, we only have a finite number of examples. Of course, this problem should be hard, right? Because sometimes in practice, the distribution can be very, very complex. Here is just one example. The density is very complex, right? And when we work with real data like this, the distribution should be much more complex. And the training target is to find that distribution in the space of all probability distribution. So essentially, this problem should be intractable, right? And the idea in practice is we use a simpler distribution to approximate this one. That is very traditional in machine learning, right? We work with very complex function, but now we use a model to approximate that, right? Here we apply to distribution. Okay, when we choose a model, it means that you are working with a family of specific model, right? That is, you can work with a set of distribution. Once we choose the form, means that you can work with this area, this set of distribution, right? And the true distribution can maybe here. And we are trying to use one of those to approximate this one, right? That is the task of the learner. You need to find one specific distribution that can approximate the true distribution, right? And when we choose this one, sometimes we call that the hypothesis space. And it is based on your experience, right? Sometimes you can use very complex model type, but sometimes you can use very simple, right? It depends on your preference or your prior knowledge, for example. Okay, and each member in that space, we often call a model, right? Or a distribution. This is just one example. When we choose the Gaussian family means that you are working with this set of distribution, right? It contains every normal distribution with parameters zeta, like this. This is just one example. Okay, once we already choose the family, the task of the learner is to find one specific distribution we denote by P zeta that can capture the data distribution, okay? The true data distribution, that can approximate the true data distribution very well. That is the task of the learner, right? Based on the training set. But this task is very hard, intractable, right? Because we only have a finite number of examples, but the data distribution can be sometimes very, very complex, right? Okay. So for the learners, in order to learn well, it needs to know what distribution can be good, right? And which one should be the best, for example. That is, among many members in this family, we need to know, we need to compare these two distributions, two members in this family, right? Which one should be better, and which one should be the best, for example. But how to say that it's the best? As you know before, when we work with traditional machine learning models, we we also need something to compare two functions, right? Which one should be better? So, what kind? How to measure? How to compare? Do you remember how
We
to
minimize.
compare? Okay, please continue.
Yes. Can to know this p theta to be best approximation for the distribution p. We need to compare between them via KL diversion to minimize this distance between the two distributions.
Yes, that's good. We use payout in this case, but the question is for traditional models, how can you compare two different models?
Sorry, can you answer me again?
Previously, for traditional models, how can you see the quality of one model, and then you can use that to compare two different models? For example, for neural network or for linear models, how can you see the quality?
Uh, we minimize the likelihood, maximize the likelihood, or
No,
the
no, no.
minimize
My question is for traditional model.
traditional model.
Yes.
For the example or the knowledge or theory about it.
No, for linear model.
For linear
Linear model.
models, we learn the theta as the parameter weight, right?
No, the question is how to see the quality of a linear model.
We evaluate that. We evaluate it via some criteria, right? Or some specific task.
Mm-hmm. What is the criteria?
Um, some things like criteria about the loss function or risk, right?
Okay, so the loss function. We were already remind us some weeks before, right? In order to see the quality of one model, one way is to use the loss function, for example, or the risk. Okay, that is for traditional model. For linear function, for example, for a neural network, we can compute the loss, and then we can use the loss to compare two different models. But now we work with distribution. Can we compute the loss? Can we? For example, in a classification problem, if we have this data set, and then you want to know the quality of this function. Okay, so let's compute the log. The loss of that on a data set, right? For example, you see, it should go here. Yeah, it should be better to. Okay, you can compute the loss based on the data set, right? Something like this. For example, if a loss function to be as 12, for example, and you can use this to compare two different functions, two different models, right? Another model maybe G. You want to compare F and G. So based on this, you can compare which one should be maybe better. Use one measure, right? It is a square error. Okay? But now it work with distribution. It is not a normal function anymore, right? A distribution. So to see which one should be better, or to see the quality, sometimes it is not easy. And you need to borrow some new tools that can help you to measure what is goodness and which is the best for that. Right? Okay. So let's return to learning problems. In fact, we are working with the density estimation problem, especially in the case the distribution is continuous, right? It is in fact we need to find the distribution we are working with, the true distribution, right? Or the full distribution. So that's why the learning problem now can be considered to be a density estimation problem. Because the density function, it is the main way to represent one distribution, right? Okay. When we choose a model represented by zeta, so the learning target is to find one specific distribution p zeta that approximate the two distribution very well, right? Or in other words, this one should be close to p, right? If they are the same, you should succeed, right? But in practice, it is not the case because the true data distribution is often very complex. But our models can be much more simpler, right? So we need to evaluate how far our model can be, right? Or closeness between those two distributions. Okay. One way to measure the closeness between the two distributions is to use KL diversion or the Kumbach-Klepler diversion, and it is defined by this formula. The expectation of this ratio, okay, the log of this ratio, where P and Q represent the density of those two distributions. We denote by KL between P and Q, and this is how we denote KL, okay? Okay, so for this definition, you can easily see that KL should be non-negative, right? It means it satisfies this equation, okay, for any distribution P and Q. And in the case, if Q is equal to P, then the KL is 0. Right? Because here it is 1, and then the overall should be 0. But for these diversions, when we change the position of P and Q, then in general, they are not the same. It is very different from other type of measure. For example, Euclidean distance, for example, it will change the position of two different variables. So the distance should be the same, right? Other L square laws like this, it will change F and Y. The result should be the same. But here for KL, it is not, right? So it means that this kind of measure is asymmetric, right? And when we use this, you are trying to measure the loss or the number of bits when we use Q to describe distribution P, right? Okay. So by this way, this is one measure so it can help us to see the closeness between two distributions. Okay, so let's return to the learning problems. We are trying to find one specific distribution that best describes the two data distribution, right? For example, in the case you choose your model to be this area, okay, and the main task is, the learning task is to find this specific distribution, right? Because it has the smallest, or it is closest to the true data distribution in terms of KL, right? Or in other words, you are trying to find the best parameters so that the KL diversion between P and P0 should be minimized. This is how we can formulate the learning problems when we work with generative model. Any question?
No.
Okay, let's return to KL. We can rewrite KL in different ways. For example, we can express this ratio, right? Because the log of the ratio can be represented by the by log p minus log p0, for example, and then we can express by this sum, right? The first sums can be expressed like this, and the second sum represent the expectation of the expectation of the log p0. Okay. So let's see this term. You can see that the first term here only depends on the data distribution, right? But the second term depends on our model, P0, right? In the training phase, we are trying to find zeta that minimize the KL reversion. So it means that the first terms does not depend on zeta and can be ignored, right? And then minimizing the KL reversion. In fact, we are trying to minimize this term. Okay. And this term, sometimes we can interpret this as the log likelihood, right? The expected log likelihood. So by this formulation, you can see that minimizing KL, it is in fact maximizing the expected log likelihood of our data. So it means that when we minimize the KL, it means that we are using one way. It is maximum likelihood estimation in statistic. Okay. In fact, we are using this way to do inference or to do trading, right? So the training problems can be formulated like this. We want to find zeta star that maximize this expected log likelihood. That's all. So up to now, you have two different formulations for the training problem, right? One is minimizing the KL. The other is log likelihood, right? MLE. And they are equivalent. But in this case, even though we know that this is the optimization problems we want to solve, but in practice, PX is unknown. The true data distribution is unknown, right? So it means that we cannot compute this quantity directly. So how to solve this problem? What is expected here? Expectation. Yeah. Well, it is in fact the situation E well E here right? We can rewrite in the detail what happened, right? Okay, so here we can see that this one represents the density of the data distribution, right? And it is unknown. Even though this form can be known, right? Can be known because we choose some form. So this one can be but this one unknown, right? That's why we cannot use it as an update for. But how we can do training? We need to use a data set, the training set, right? If we have a training set, means that you have some sample from the data distribution, right? And then we use that to approximate this expectation. This is one way. We approximate this one by using the data set D. So you can compute the average of log P zeta x for every x in D. We use a data set to approximate the true objective, right? And then we can use this quantity for training. And these quantities, you can see that this is the log likelihood, and this sum, this average, sometimes we say that the empirical log likelihood, right? Because we compute from a data set. And of course, it is very similar with the empirical loss or the training loss for other model, right? But here we work with distribution. Okay, so now if we use a data set, then the training phase can be formulated as this problem. We will find the parameters that maximize this average computed on a training set, right? That's all. And of course, by this way, you can see that because the products, the sum of the log, it is equal to the log of product, right? So if we are working with this, essentially, we have some assumption about the data. They should be independent, right? So then the product here can be represented by the joint distribution of the example in the training set. And we are trying to maximize this likelihood, right? Okay, so let's take one example. Let's return to the data set before. In the case, if we want to estimate the height, right? When we have this data set, and when we choose the Gaussian distribution, the Gaussian model, right? Then the learning phase is to find mu and sigma based on a training set D, right? Okay, so let's apply our previous idea. For example, the learning can be represented by this, can be transformed to this problem, right? Okay, so for this model, the learning task is to find mu and sigma, right? And in order to work with this, it needs some way to compute this log, right? This log, okay? For this kind of models, we already know the density. So let's denote fx given mu and sigma to be the density of this family, right? Then for any given example, this quantity should be the likelihood of one observation, right? And when we have many observations, this quantity we can consider to be the likelihood of a data set. Okay, then MLE can help to train a model, to train this model. That is, we are trying to find these parameters that maximize the likelihood of this data set, right? Okay, so let's do further. If we assume that the data sample are independent, then we can write PD to be the products of PXI for every XI in the training set, right? So the training problems can be formulated by this way. We are trying to maximize this product, right? And then when we use the explicit formula for the density, we can write the new problem to be like this, right? We're trying to maximize this. And of course, we can apply the log tricks to transform this objective to another objective function. Because here we are working with a maximization problem, right? The solution for these two problems should be the same. So that's why we can use log here. And when we use log here, log of the products can be represented by the sum, right? Okay, so here we can write the training problem up to now is very simple. And of course, from this step, we can use some very simple ways to solve this problem, right? Because here, the main target is to find mu and sigma. And this function is very simple. You can take the gradient and then solve the gradient to be 0. And then you can find the optimal solution to be like this, right? This is just one example to show how to train a simple model based on MLE. Okay? And of course, for more complex models, the training is not easy like this, right? Do you have any question?
No.
Okay. So let us discuss further how to train models. Let's return to the training problems, because the true data distribution is sometimes can be very complex, and in practice we need to use some other models to approximate that, right? And this model can be simple, and we can use that in practice. And we hope that these models can approximate the data distribution, right? Can approximate well. That is our hope. But how? The first question is how to choose this model family. For example, we can choose Gaussian model, Gaussian family, as we take example before. How about that family?
Simple.
Too simple. Yes. And in practice, because the data sample can be very complex like this, right? It means that the data distribution is also very complex. So the model family should be complex enough. Then we can hope that it can approximate the true data distribution well, right? Okay. So what model? What family we should use? We already know one family, right? the Gaussian family or the normal family, right? That is what one family, one option. But that option is too simple. Another option is Gaussian mixture model. Sometimes we call GMM. This is a very classical model in probability. And in this models, we have a very special assumption. We assume that the data sample come from K Gaussian distribution. In the Gaussian family, the data sample only come from only one normal distribution, right? But now in GMM, we have K different Gaussian. And the data sample should come from one of those, right? So in this case, the distribution can be more complex. This is just one example. This is a GMM with two components, okay? This represents the first component and this represents the second component. And you can see that the density now more complex than Gaussian, right? Okay, in GMM, we have our assumption is the following. We assume that each data instance is generated by one of those K Gaussian by the following generated process. Or in other words, in order to generate one sample, we need to do two steps like this. In the first step, we take the component index Z that will generate the data sample, right? Then we use that distribution to generate X. That's all. Only two steps. So every sample in this model should be generated by this process, right? The first step is to choose which distribution will generate the sample. Then use the parameter of that distribution to generate X, right? Okay, here we denote here categorical means it is a special kind of distribution. Categorical distribution. Okay, with parameter phi, it represents the probability that we choose one distribution among many different distributions. Okay, so for this models for GMMs, we can write the density in an explicit way. For example, we denote by Qx given mu sigma phi. This is the density, okay? And the density of this mixture, it is in fact the convex combination of the density of those Gaussian distributions. Okay? Here we denote n x, given mu k sigma k to be the density of one component, one Gaussian component, right? And phi k here, it represents the probability that we will pick the k component, right? So it means that phi k should be from 0 to 1, and all of those phi should sum to 1, right? And this constraint means that this density should be a convex combination of the density of every other component. Okay? And each component can be represented by the density like this. It is the density of the Gaussian distribution in a high dimensional space, right? Okay, so in this case, you can see that we have two different variables. One is Z and the other is X, right? X is observable, but Z sometimes hidden, right? So we have two variables. Okay. Okay. So for this kind of models, it can be more complex and provides you another choice, right? To be easier. Okay. And this family, it has very special properties. Even though we can write the density explicitly like this. If we choose k to be 1, what is that? If k is 1, GMM now. What is it? In this case, you only have one component, so it is a normal distribution as usual, right? But when you choose k more or greater than 3, so GMM can be very complex. For example, if we choose k to be 2, the density might be here, but when k is 3, the density is like this, right? So you can see that the densities should be more complex as we increase scale, right? So it means that when it is complex like this, and we use this to approximate the unknown function, the unknown distribution. So, how about your opinion? Assume that the density of the daily state can we use GMF to approximate.
Sorry, I can't hear anything. I can't hear anything.
How about your opinion?
Sorry, I can't hear anything. So can you ask me again? Sorry.
Okay. The question is for offline student only.
Apply what?
How are your opinions? Can we use GMM to approximate this one?
Sorry, I
Or your
can't hear.
Sorry? KL? No, the question is, can we use GMM to approximate this distribution?
For the k is equal to 1 component, right? Sorry.
Sorry, the question is for offline students.
Your question is apply. Can we apply GMM for this k equal to 1 component, right?
No, the data distribution is more complex. I just draw on the board.
Yes, why not? I say yes, why not?
This is a special property of GMM. It can be very strong. It can approximate any smooth distribution if we use a large number of components enough. So that's why GMM are universal approximated. So it means that it can be a very good model, very good choice to have a to approximate the true data distribution, right? In theory, we there's some work that show that this kind of model is very strong approximate. It can approximate any complex distribution. Assume that the density is smooth, for example, right? Okay. When we increase K, GMM can represent very complex model, right? Now we move to another variance. It is called infinite GMM. In the previous case, these GMMs only have K component, right? And K is finite. But now, if we use an infinite number of components, how we can build the density, and how we will build that model, and what is the capacity of that model? Here is just one example. One way to build infinite GMM arrays, we just replace the categorical distribution before by a Gaussian distribution. That's all. So for this model, each example is generated by one of those Gaussian by the following process. That is, in order to generate one example, right? We need to do these two steps. In the first step, we choose the index, the component index Z from the normal distribution, right? And then based on that index, we use the mean and variance of that distribution to generate X. That's all. This is another variance from GMM, right? But here, Z is a sample from the normal. So how about the value of Z? How many values Z can receive?
Infinite.
Yes, infinite. That's why we have infinite GMM. Okay, so this step are trying to work with this distribution, right? the distribution of Z. Okay, and this step, we are working with the normal distribution condition on Z, right? That is, we are trying to represent this probability. We are trying to work with the distribution of X given Z, right? Okay, and in practice, in order to produce a distribution something like this and represent the infinite number of Gaussian, one way is we can use a neural network to produce mu and sigma. Okay? Here, mu and sigma represents a normal distribution. And the neural network can be represented by zero. For example, the weight, right? The weight of the network. Okay, so it means that we can combine probability and neural network to produce something very strong, right? Infinite GMA. How about its capacity? Of course, it should be very strong in theory, right? When we use only a finite number of components, GMM can be universal or approximated. But now, when we use an infinite number of components, so this should be very strong, much more stronger, right? So you can see that these models should be very, 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 very strong. If we use a suitable neural network, then this model can approximate any data distribution, right? Okay, do you have any question?
No.
Otherwise, we should have some minutes break, okay?
lao à mấy hết
Okay, so let's return to our lecture. But before that, let's see, let's do some enumeration to see the attendance. Alisa, you, right? Mhm. Yeah. So how can how should I pronounce? Mm. Okay, it's hard for me. Hamidova. Oh. Đức Anh, Nguyễn Đức Anh. I hear. Hải Anh,
Dạ có ạ.
Lan Anh, Lan Anh, Mai Anh, Quốc Anh, Quốc Anh.
Yes, teacher. Yes, teacher. I'm here.
No, Bùi Quốc Anh.
Em xin lỗi thầy. Sorry, that's not my name. Sorry.
Okay, so you may be Hoàng Quốc Anh,
Yes, that is me.
Tiểu Anh, Nguyễn Tuấn Anh,
Yes, I'm here. I'm here.
Dương Việt Anh, Ngô Việt Anh, Trương Gia Bách, Thái Bình, Mạnh Cường, Huỳnh Văn Cường, Hoàng Đăng, Ngô Hoàng Đăng, Nguyễn Hoàng Đăng,
Em có như thế ạ. Ngô Hoàng Đăng có.
Trương Thị Đào, Hà Đạt. Hà Đạt có không? Quốc Đạt, Thành Đạt, Đinh Quốc Đạt, you are here. Okay, Hoàng Thành Đạt, Phùng Tiến Đạt,
Yes.
Hà Trọng Đạt, Hà Trọng Đạt, Tuấn Đạt, Lê Hồng Đức, Nguyễn Tiến Đức, Trần Tiến Dũng.
I'm here.
Hiếu Dũng, right?
Yeah.
Cảnh Dương. Hoàng Dương. Minh Dương.
I'm here.
Đăng Duy.
Yes, I'm here.
Minh Hà.
Yes.
Quang Hà.
Có.
Thu Hà. Hoàng Hải.
Có.
Hữu Hải. Song Hào. Việt Hòa. Huy Hoàng. Nguyễn Trọng Huy Hoàng. Minh Hoàng. Nam Hoàng. Nam Hoàng. Đức Hưng. Đức Hùng.
Yes, I'm here.
Thầy ơi, của em là Hoàng Minh Hoàng vừa mới bị qua tim.
Ok. Nguyễn Mạnh Hưng.
Có.
Quốc Hùng.
Có.
Hương. Quang Huy.
Dạ có.
Phạm Quang Huy.
Thầy ơi, em điểm danh Đinh Thị Hương vừa rồi.
Ok. Minh Huyền. Duy Khánh. Chu Kiên.
Có. Có.
Trung Kiên.
Trung Kiên hay Chu Kiên ạ?
Trung Kiên.
Dạ em có ạ.
Tuấn Kiệt.
Có.
Phạm Tuấn Kiệt.
Có.
Nguyễn Tuấn Kiệt.
Có.
Đình Lộc. Hoàng Long.
Hoàng
Mai
Lê
Hoàng
Tiến
Long.
Long. À, không.
Tiến Long.
Có.
Lê Văn Luân.
Yes, I'm here.
Tùng Lương.
Dạ có.
Xuân Mạnh.
Yes, I'm here.
Anh Minh.
Dạ em có.
Vương Hoàng Minh. Khánh Minh. Ngô Quang Minh. Quang Minh. Viết Minh.
Có.
Thanh Nam.
Anh Nam có ạ.
Văn Nghĩa. Nghĩa. Duy Phong.
Có.
Đức Phúc.
Dạ em có.
Đình Sơn.
Dạ
Đình Sơn.
em có.
Thế Sơn. Phú Tài. Như Thái.
Có.
Vũ Quốc Thái,
Có ạ.
Quang Thắng, Phương Thảo,
Dạ em có.
Đức Thịnh, Thịnh, Minh Thương, Mạnh Tiến, Việt Tiến, Huyền Trang, Quỳnh Trang,
Em có ạ.
Thu Trang, Thùy Trang, Minh Trung,
Có.
Ngọc Trung, Đức Tuân, Nguyễn Văn Tuấn,
Có.
Kim Tuyến, Kim Tuyến, Thu Uyên,
Em có ạ.
Đại Việt, Hoàng Việt,
Em thưa thầy, lúc nãy máy em nó không bật được mic, em phải chuyển điện thoại. Em là Mai Anh ạ.
Ok.
Em thấy là em bị qua tên mất, em là Hồng Đức.
Gì Đức nhỉ?
Em là Hồng Đức.
Hồng Đức.
Em thưa thầy, em lúc nãy cũng có một chút trục trặc máy móc nên là em xin điểm danh vào muộn. Em là Mai Hà Đạt.
Ok.
Em thấy nãy em không ai bị mít mất thì em tên là Bùi Việt Hòa.
Em thưa thầy, vừa nãy em cũng bị miss mất ạ. Em là Hoàng Tiến Đạt ạ.
Okay, so let's return to our lecture. Okay, so let's return to the model we studied before. For example, GMM. If we want to learn GMM from in practice, okay, so one way is to use memory, right? For example, we can find the parameters of GMMs by maximizing the likelihood, the log likelihood on the data set, right? Because here we work with GMM, so we already know the density function for this family, right? For example, this is the density function, and the parameter here, zero, should consist of many different parameters. For example, phi, mu, and sigma. for each component, right? And of course, zero denotes all of those parameters that represent the model. Okay, but now even this, we already know the form for the density. But when we use this form into this formula, it can result in a very complex objective function. Because for each x, each observation, we need to compute this density, right? This log. Okay. And this log, it is in fact, px can be represented by p zeta x z, where z here represents the index, right? The index of the Gaussian. In this case, in our case, z can be one of the k different values. But in practice, sometimes z can be very, very huge. The number of possible choice can be very huge, right? Okay, for example, when z belongs to this set, that means that these sums should have a large number of terms, and it is very expensive to compute this value, right? This term. So that's why, even though sometimes we already know the density of the distribution, it's very, very hard, very expensive to train a model. So that's why, in practice, some approximation is needed, right? Okay. So let's consider more detail about the likelihood. For each example x, its likelihood is log p zero x, right? And we can express this into the sum for every z, every value of z, right? This is just a probability from probability, right? The marginal probability can be expressed as the integral or the sum over other variable, right? Okay. So from this one, by multiply with one quantity and divide by the same quantity, right? Then we can rewrite this sums to be the expectation according to QZ. And QZ here can be any distribution, right? So the log likelihood now can be expressed as the expectation of this ratio. Okay. So let's observe this. Here is the log expectation of the ratio. And the log function, it is a concave function. So we can apply Zen-San inequality. It means that the log of the expectation is often greater than or equal than we can put the log into the expectation. Okay, that is we try to exchange these two quantities, these two operations, because the log of the sum can be very hard to compute in practice, right? So we try to move the expectation outside. Okay, so by Zen-San inequalities, can be expressed. It is in fact greater than or equal to the expectation of the log of this ratio. Okay. Now these quantities can be much more easier to be computed in practice. And this quantity can be represented by the addition of these two terms, right? And these two terms we often call that to be the elbow, the evident lower bounds for the log likelihood. Okay, and this quantity is very special. It can be computed, it can be approximated very well in practice compared to the log here, right? So that's why this quantity is very often used in practice. Okay, so those observations show that the log likelihood is at least the elbow, right, for any x and any distribution Q, right, over D. In the case, if we choose QZ to be the posteriors of Z given x, for example, then the log likelihood is the same with the elbow. Okay, so that's why the elbow here is very good quantities, and it can help us to do some computation in practice. Okay. Okay, in practice, sometimes the posterior is easy to confuse. So we can use the posterior. We can use the elbow here. For example, we can use the elbow here in the case if this quantity is easy to compute. The posterior distribution. Okay. We can express anything here. Okay, but in most cases, when the distribution, when the models we choose is very complex, so it is not easy to compute this quantity because each one here can be very complex, right? So in that case, how could we do? How can we do? How can we compute this? Even compute the log likelihood on a data set is sometimes very difficult, right? One idea is we knew the methods. One method it is variational inference. Okay, and the idea of this method is very simple because the density of our model can be very complex, right? We cannot work with that directly. We can use another simpler function, simpler distribution to approximate our model. That is the idea. That is known as variational inference, right? Okay, so for that simple distribution, we can it can be represented by phi, and we can consider phi to be the parameters of that model, right? And sometimes we call that the variational parameters, right? Okay, and when we use this, the learning phase is then to find the best value of phi so that Q can approximate P0 as best as possible, right? That is the idea of VAE. Okay, so essentially, in order to work with a data, we need to find it, right? That is our original learning problem, right? And in practice, when we choose a model parameters analyzed by here, for example, it means that we are trying to indeed to approximate this one, right? We are trying to we hope that this model can approximate the two distributions as well. So this is the first approximation. But this approximation is still very hard to create one, right? And the idea of VAE, we use a more simpler model here. divided by 5. Okay. And we use this marker to approximate. Here. Okay, so we have one more approaching. And of course, here to be simpler than easier. Okay, and we use both for the training phase. In the training phase, we are trying to learn this, right? To approximate the two data distribution, but the data is still complex. That's why we use another distribution to help us to learn this. Okay, when we choose Q, then the elbow can be written by this. Okay, for every z, for every xi, we will use q phi i's, right? That means that for each example in a training set, we will use one distribution q that can help us to approximate p, the log likelihood for that example. Okay, then our learning target is to maximize this, right? To maximize this quantity, okay? And of course, from these quantities, you can show that maximize this, it is in fact equivalent to minimize the KL reversion, because the log likelihood of X can be expressed as the sum of these two terms, right? One is the KL and the other is the elbow. Okay. So maximizing this, it is similar with minimizing the KL, right? So that's why we can work with one of those in order to train the model. Do you have any question?
Sorry, I have a question.
Yes.
Why we need to add the KL after the elbow?
Why we need to add here, right?
Yes.
Okay. No, we do not add something more here. They are equivalent. Another expression for the log likelihood. This is the nature of the log likelihood. We can write the log likelihood to be the sum of the elbow and the KL. Okay. This is not the artifact we add more, right?
Okay, I see. Yeah, I understand. Okay. Thank you.
Any more question? Yeah.
No.
Yes. Because directly finding this sometimes can be very difficult. So we use another family, simpler family, to approximate that. That is the main idea of VAE. because this is a simpler, then we can work with that easier. For example, P0 here can be GMN, but now we choose Q to be a Gaussian, for example, right? So Gaussian, we can write very explicitly. Well, what is the MLE, or what is the distance, the KL distance, for example? Easier to work with, right? For example, in this figure, Q here represent one Gaussian, but P0 here is Gemin. You said about zero. Yes, when we approximate this, it should incur some error. We cannot avoid, right? But in practice, VI it is often very efficient for some model. Okay, so let's return to the elbow. When we use Q here, and we are trying to maximize this sum, right? So here, the problem now, we have more parameters to be optimized, right? One is zero, another is 5, the variational parameters, and the parameters for the model, right? So now we have two set of parameters. And the training phase now should require to find all of them, right? So that is it should be more expensive. And the idea to train this is to use some idea from gradient descent. For example, we do two main steps. The first step is to find the variational parameters, and based on that, we can find zero. And then we do these two steps many times until we can obtain a good parameter for the problem. But it is just the main idea. Based on this objective, we can compute the gradient with respect to phi, right? We update the phi. And then, based on phi, we can compute the gradient with respect to 0. And then we can update the model parameters, right? It isn't just the idea. Okay? It depends on your models. This objective can be more complex. Any question? Yeah. Mm. 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 Good question. Do you see his concern? his concern is we are trying to use Q5 to approximate P0. For P0, for this distribution, it is a conditional distribution, right? The distribution of Z condition on X, given X. Then we have this distribution about Z, right? So this distribution depends on X. But here we use a distribution that seems not depend on X. But why? That is his concern. And by this way, we may miss some information from X, right? How about your opinions? Mm-hmm. How about the other idea?
Can you ask again, please?
Yes?
Can you ask the question again, please?
Okay, so his question is, why we use a distribution which is not depends on X to approximate another distribution which depends on X. This one depends on X, right? But here we use this one to approximate P, but Q does not depend on X. Okay. To answer this, you can see that P0, PZ given X. It means that for each X, we have one distribution, right? For each X, we have one distribution, P0. It is a distribution, right? So it means that this distribution can be approximated by some other things, right? And here we call phi. Okay, so for each X, we have this distribution. Another X, we have another distribution. Right? And now we use another distribution to approximate that. How about the distribution? We use the same family. And we use the same idea. This should be different from this. How about this one? Should be different. Right? That means that in it another parameter will represent that distribution. So this one will be different. So what do you mean? X1, we use 5 1, X2, we use 5. So for each example, we require 5. And this number, which one depends on that. Right? It is a variation of parameter. For X1, we need to find 1. X2, we need to do 3. Right? And impact for impact. How can we define this one? And finally, this kind of this impact depends on that. Okay? For each side, we will have this kind of pattern, right? So that's why in this formulation, we should interpret that phi should depends on x, right? Implicit. If we are trying to use this to approximate this one, right? Okay. So that's why in this formula, we use phi I, right? That corresponds to xi. For each observation, we use one set of parameters, variational parameters that correspond to that x, right? So in a training set, if we have an example, so what it means, the number of parameters here, how many? From phi 1 to phi n. We can have to represent different distribution, right? But we only have one zeta. So by this way, VI suggests that the number of variational parameters should be linear in the number of samples in a training set. That is the property of VI. And you can see that these parameters implicitly depends on those training samples, right? Depends on x, a function of x, right? Okay, you are clear about that? Yeah.
Yes, thank you.
Mm-hmm. Mm-hmm. Yes. Mm-hmm. Yes, by this way, you can write something like this. For each act, we will have 5 acts, right? So in that case, we can write the low bound, therefore can be like this. Q, I, X, D, right? If they in linear form. Okay, any other question?
I have a question.
Yes.
I just see. I just say for x phi I, it will depend on x I, right?
Yes.
So that means we will have the how to say x I we will have we need to optimize specific thing for the QI, right? For the VAE, right?
Yeah.
Oh, so but I think it could be very slow, right? Because for the XXI, we need to find the X distribution of theta depends on XI. So I think it could be quite slow, right?
Yes, yes, of course. It can be slow, can be
Yeah.
costly.
Oh,
Because the number of parameters here is can be huge, right?
yeah. Okay. Okay, thank you.
Okay, so that is VI. That can help us to work with more complex model. If we choose a complex model, sometimes MLE is hard, and then in that case, you can borrow some idea of VI to for the training, right? So it can be very easy to be used in complex model, and in practice, we often observe that it is efficient. Okay. However, it has some disadvantages. As we discussed before, sometimes it can be hard to choose a good variational family. Sometimes, okay. Especially in the case we do not know the form of this posterior distribution. Sometimes we know this explicitly, but sometimes we cannot. So, how to choose a good variational family? In that case, it is very hard, right? Because this distribution sometimes very complex. And in the case, we can have a good variational parameters family. But for inference, you can see that for each new example X, and given the models, if we want to do inference for X, then we need to solve this optimization problem again. Because we need to find to estimate phi that correspond to this new example, right? And of course, it is a maximization problem. And sometimes it can be very hard or costly. So that's why VI is expensive, right? Even for trading and even for inference. And another thing is, for each example, it requires one parameter. So the number of parameters here scale with the size of the training set. Very huge, right? And it can be it can cause some issue. For example, overfitting, for example, sometimes. Let's take just one example. If we use VI for GMM, then the number of parameters can be like this: m, k, n squared, where n is the size of the dimensions, the number of dimensions, for example. So in this case, you can see that it is very huge, right? Very expensive. So some years ago, 10 years ago, there's a very brilliant idea that can help us to overcome those limitations. It is known as amortized inference. Okay, in VI, each example requires one parameters, right? Or a set of parameters. And this means that we cannot scale VI for a large data set, for example. And this way can lead to some situation like overfitting. Okay, and the idea to overcome this is we can use only one single neural network to do this. And the idea is the neural network can help us to map from one X to the variational parameter. And that neural network only use one set of weights, right? And the set of weight is shared for every example. And the size of the weight can be fixed, right? Even though the size of the data set is very huge, for example. That is amortization. So essentially, given one data sample, we just put that through the neural network, and the neural network can produce the parameters for the variational distribution, right? That's all. Okay, so for neural network, we have a set of parameters W, and this can be trained, right? Can be trained based on a data set. So after training, we can use that to do inference. So by this way, no need to do optimization, right? That is very different from VAE. Okay, so it means that it is very efficient, right? After training. In the training phase, it can be costly, but inference is very easy, right? Efficient. Okay, so for VI, we were trying to maximize the log likelihood or the lower bound, right? According to the parameters of the model and the variational parameters. But now we change those variational parameters by the weight of the neural network, right? And of course, we can consider that to be a set of parameters, and we can use SGD to maximize this objective, right? For example, by this way, these are some steps in order to have to maximize this function. Okay. And when we use SGD, each step we can compute the gradients with respect to parameters, right? For example, we compute the gradient with respect to 0 or with phi, for example, right? And we use those gradients to update the parameters. Okay, but all those, these are very simple ideas, but sometimes for complex models, the gradients can be very hard to compute accurately. Especially in the case if we use a neural network combined with a probabilistic model. So overall, this sum can be very complex. And then if we want to compute the gradient, sometimes it can be very hard. Because here, the elbows, it is the expectation, right? And in practice, you need to approximate. A good approximation can lead to better training. But a bad approximation can lead to unstable training, for example. Very hard to converse. Okay. So the idea to have to train easier is to use reparameterization trick. And the idea is very simple because the objective function is often like expectation, right? So we need some way to compute it or to approximate it, right? So let's consider the case we want to compute the expectation of RZ according to Q phi. Or in other words, we can write something like this, right? And let's consider the case Q here to be a Gaussian. Okay. And for a Gaussian, it has a mean, mu, right? And variance. And last, just consider the case the variance is simplifies to be sigma squared, for example. Okay, so assume that the variational distribution to be like this. Then for every sample Z from this distribution, it can be represented by the sum of mu and sigma epsilon, where epsilon here is a noise, a white noise. Okay, means that it follows the Gaussian distribution with mean 0 and variance 1. Okay. This is a standard knowledge in probability theory. Okay, so now we use this for this expectation. Then we know that the expectation according to Z can be translated to the expectation over epsilon. And here, these quantities can be much easier to be approximated in practice. And one special thing is epsilon here is fixed, does not depend on the parameters, right? But here, Z depends on phi, the parameters we are trying to optimize, right? And if we are trying to take some sampling, there should be some variance, very high variance in the sample. So if we just take some sample from this one, it does not depend on the parameters we are trying to optimize, right? So it means that the sample, the expectation can be much more stable, easier to estimate. Okay. And based on that, we can take the gradient, right? The gradient for phi, and it can be translated to this one. Okay, so it means that we can compute, we can approximate the gradients by this trick easily. Okay. We just take some sample from the white noise, from the Gaussian distribution, and then compute the average of the gradient of R, for example. So that's all. That is the truth. And it can help us to work with this one. It can help us to compute the gradient of this quantity. Okay, and then can help us to do SGD. Okay, so that is the trick. And from that trick, we can write the objective function to be this sum, where the first term represents the log likelihood conditional on Z, and the second term represents the KL diversion between our variational distribution and prior distribution over Z. Okay. So this means that when we are trying to maximize the elbow, it is equivalent to maximize P zeta x given D, while minimizing the distance between these two distributions, right? But what it means? What it means when we are trying to maximize it, when P is a Gaussian, it means that we are trying to recover the original input x. Okay. Okay. So how to do this? Because here, this conditional distribution sometimes can be very complex. So one idea is we can use a neural network to learn this. Okay. Given one Z, it can produce one X, for example. Okay. And the other part is to use another neural network to represent the variational distribution. Given one X, it produces one Z. Okay. It produces the parameters of this distribution. And that neural network, we call that the encoder. Okay. So the role of the encoder is to map from one data point to a latent vectors, Z hat. And Z hat here represent one example from the conditional distribution we are trying to work with, right? We call this a latent vector because sometimes it can help us to represent very meaningful things in the data sample. Okay, and then we use another neural network to work with this conditional distribution, right? Given one Z, it can produce X following this distribution, right? Okay, that means that we use a neural network to reconstruct the input, the original input, right? And we call this the decoder. Okay, that is the idea to work with this kind of complex model. And this idea composed of matters. It is a VAE, just appeared about more than 10 years ago. So by this way, we just, for the training phase, we just maximize the elbow, right? And the elbow can be written by this one. And we are trying to maximize that. And now we can see that the first term, it represents the reconstruction error when we try to reconstruct the original input by the neural network, right? How about the second term? We are trying to push the prior over Z to be close to the variational distribution conditional on X, right? Okay, for training, we can use SVD and the trick we studied before, right? The idea is very simple like this. But in practice, VAE can work very well. That is very interesting. So we already have one way to have to train a model to approximate the true data distribution, right? And after training, we can use the decoder to generate new samples, right? While the encoders can help us to produce new representation for any given input. So the two neural networks play two different roles, right? Very interesting. Do you have any question? Here are just some example. These are some figures after training. The decoders that can help us to generate some new pictures about the numbers. These are just some example generated about more than 10 years ago, the first version of VAE. But some years later, we can train a much more better models that can help us to generate more complex images like this. Okay. It is known as VQVAE. And up to now, VQVAE is still used in some modern systems. For example, when you use stable diffusion or some other kind of system, we are still use VQVAE as an intermediate step Okay. So we can see that VAE can be very, very efficient in practice. After training, we can use the decoder to generate new sample, right? New image, for example. And in practice, people often observe that the image generated by VAE can be very diverse. That is a very, very important properties. However, the image produced by VAEs sometimes can be blurred. This is a disadvantage for this kind of model. Do you see why? Why it often produces some blurred image? Okay. So I think that's all for today. Do you have any question? It seems too much. Okay, that's good. No question. Everything is clear, right? So we're going to stop here. See you.
Thank you.